Prelims in Algorithms and Complexity. Hi everyone! Hi Prof. Doc Alagos. Now, I'm going to present about AR or Performance Enhancement Elective Learning Outcomes. Presented by me, Herby G. Estrella, PSCS 3 New Mode First Year, Second Term, 2023-2024. The first question is, describe superscalar architectures and their advantages. Familiarity. My answer is, in superscalar architectures, a processor design known as superscalar architecture enables multiple instructions to be carried out concurrently by several execution units. Performance is improved with this design by increasing the throughput of instruction execution. Superscalar architectures use instruction-level parallelism to execute several instructions in a single clock style, which increases process performance overall. This is achieved by concurrent decoding and dispatching of instructions, but create effective superscalar processors require solving issues with resource distribution, verifying dependencies, and making the most use of execution units that are available. For comprehension in computational science, one must grasp the fundamental of superscalar structure design. These designs allow many instructions to be executed at once, increasing processing speed, a solid understanding of superscalar architectures, and the difficulties in creating effective superscalar processors, such as resource allocation and dependency verification, is essential for students studying advanced processor design concepts. The benefits of using instruction-level parallelism are shown by these systems, which enable simultaneous instruction execution inside a clock cycle. Students studying superscalar architecture know how hard it is to create efficient processors. They should be aware that resource allocation must be conservative, numerous execution units must be used sparingly, and sophisticated dependency checking is necessary. The second one is explain the concept of branch prediction and its utility. Familiarity. Branch prediction is a vital element in contemporary processor design, addressing the performance consequences of conditional branch instructions. These branches may cause delays in instruction execution, since the processor might lack knowledge of the correct branch direction until the branch instruction is executed. Techniques in branch prediction seek to anticipate the outcome of a branch instruction before resolution, enabling speculative execution along the predicted path. This approach contributes to sustaining pipeline efficiency and overall performance by mitigating the impact of branch mispredictions. Effective mechanisms for branch prediction incorporate considerations of historical patterns and dynamic behavior, aiming to enhance accuracy and contribute to the efficiency of speculative execution in modern processors. In the realm of computational science, familiarity with branch prediction involves understanding its role in alleviating the performance impact of conditional branch instructions. This encompasses comprehending how prediction mechanisms anticipate branch outcomes before execution, preserving both pipeline efficiency and overall system performance. Students recognize that conditional branches may introduce execution delays, and branch prediction aims to forecast outcomes before resolution, facilitating speculative execution. This comprehension extends to the dynamic nature of branch prediction, adapting to diverse execution scenarios for heightened accuracy. The third one is characterize the costs and benefits of prefetching. Familiarity. My answer is prefetching serves as a tactic to to diminish memory access latency by retrieving data from slower memory and storing it in a faster cache before its actual utilization. Although prefetching has the potential to boost performance by ensuring prompt availability of necessary data, it is not without associated costs. For example, prefetching may result in additional consumption of bandwidth and energy, and misguided prefetching decisions can result in the squandering of resources. Achieving an optimal system performance necessitates a delicate equilibrium between the aggressiveness of prefetching and its efficiency. Within the domain of computational science, familiarity with prefetching entails recognizing its role in lessening memory access latency. A comprehensive understanding of costs and benefits related to prefetching includes acknowledging potential drawbacks like heightened bandwidth and energy usage. Students comprehend that prefetching is a strategy designed to fetch data from slower memory in advance, storing it in a faster cache for anticipated future use, thereby contributing to enhanced system performance. Simultaneously, they grasp the potential drawbacks, encompassing increased demands of bandwidth and energy. Attaining a harmonious balance between aggressiveness and efficiency of prefetching emerges as a pivotal facet of optimizing system performance. Students can gain insights into the nuanced considerations inherent in prefetching, emphasizing the significance of fine-tuning this technique to guarantee optimal performance across diverse computational scenarios. The fourth one is explain speculative execution and identify the conditions that justify it. Familiarity. My answer is speculative execution entails the advanced execution of instructions based on predictions made by the processor, aiming to overlap the execution of independent instruction and conceal potential latencies. However, it introduces complexities, including the necessity for meticulous handling of inaccurate speculative results to guarantee program correctness. This technique is commonly deployed in conjunction with branch prediction to optimize performance, particularly in scenarios where branches lead to pipeline stalls. Proficient management of speculative execution significantly contributes to overall processor efficiency and responsiveness. In computational science, grasping speculative execution involves comprehending in function in executing instructions before their actual need, guided by predictions. Recognition of conditions justifying speculative execution, especially in situations where branches might cause pipeline stalls, is essential. Additionally, students should recognize the imperative of effective management of speculative results to uphold program correctness. Speculative execution is acknowledged as a strategic tool for enhancing processor efficiency and responsiveness, emphasizing the need for a judicious balance to navigate the complexities introduced by the speculative nature of these executions. 5 is discuss the performance advantages that multithreading offered in an architecture along with the factors that make it difficult to derive maximum benefits from this approach. Familiarity. And my answer is multithreading optimizes performance by enabling a processor to concurrently execute multiple threads, resulting in improved source utilization and increased throughput. However, extracting maximum benefits from multithreading encounters challenges including the management of shared resources, contention minimization, and efficient thread synchronization. The effectiveness of multithreading is contingent of the workload's nature and the capacity to parallelize tasks. Striking a balance between the advantages of concurrency and the associated overhead is crucial for performance optimization in multi-threaded architectures. In computational science, familiarity with multi-threading encompasses a discussion of its performance benefits, emphasizing enhanced resource utilization and heightened throughput. Understanding the intricacies linked to multi-threading, such as shared resource management and contention minimization, proves indispensable for maximizing benefits within a specific architecture. Students recognize that multi-threading empowers a processor to concurrently execute multiple threads, particularly beneficial in scenarios like scientific simulations and data-intensive applications. The advantages includes better utilization of CPU resources and increased throughput. This comprehension equips students to discern the nuanced trade-offs involved in harnessing multi-threading for optimal system performance. 6 is describe the relevance of scalability to performance, familiarity. And my answer is, scalability is a critical factor influencing system performance as its workload expands. A scalable architecture adeptly manages growing demands by seamlessly incorporating additional resources or nodes. Attaining scalability necessitates the design of systems capable of expanding without sacrificing performance. Crucial elements like load balancing, communication efficiency, and resource allocation actively contribute to scalability. Recognizing and addressing scalability issues is imperative to ensure that system adeptly adjusts to scaling workloads, avoiding diminishing returns or performance bottlenecks. In computational science, familiarity with scalability encompasses an understanding of its pivotal role in efficiently handling increasing workloads. This involves acknowledging factors such as load balancing, communication efficiency, and resource allocation, all of which contributes to a system's ability to scale without compromising performance. Students should recognize scalability as the system's capability to manage growing workloads by adding resources or nodes without compromising efficiency. They understand that factors like load balancing, communication efficiency, and resource allocation are vital contributors to achieving scalability. Students should comprehend the significance of scalable architectures in adapting to mounting computational demands without encountering diminishing returns or performance bottlenecks. This knowledge empowers them to proficiently design and evaluate systems capable of scaling efficiently in response to evolving computational requirements. Thank you for listening. Please comment down below what are your more questions submitted to Prof. Doc Alagos. Thank you for watching.